the goal of the talk is going to be to introduce some results, but also talk a lot about maybe heuristics and emphasize that perhaps more than the theorems. But I want to start with a result of Sarah's from a few years ago. About polynomial configurations in finite fields. So what does it say? I'm going to take integer polynomials linearly independent and with zero constant term. And there exists constants c and gamma, such that fq is a finite field with sufficiently large characteristic any subset of this field, number of configurations is about what you'd expect from a random set. To the n plus 1, q to the n minus 1, and then an error term of the size q to the 2 minus gamma, and gamma's constant depending on these polynomials. Okay, so at least given some finite polynomials, once the characteristic of a finite field is large enough, they said the number of configurations of this kind is what you'd expect from a random set plus some lower order term. And okay, so one, I guess, consequence of this is if the set A does not contain any configurations like this, then it has to be small. So to assume, I'm going to assume the configuration is non-trivial, so I'll say if it doesn't contain a configuration of this kind, where all of those are distinct, or now the n plus 1, then A with some constant depending on the polynomials is of size plus q to the 1 minus, I think that's right. Okay, so the polynomial similarity theorem should say that if A with a set of positive density, then we'd expect polynomial configurations. Here with linear independence, we don't see anything, we get much stronger results, that there's some power saving in polynomial similarity in the case of linearly independent polynomials over finite fields. So what I want to start by doing is explain maybe how you can guess this result from some things that are known dynamically, and then using other dynamical results as a guide, get more combinatorial results over finite fields. So, okay, as written here, it maybe doesn't quite look like ergodic theory. To actually prove this result, there's some induction process, and it's easier to, instead of looking at configurations lying all in the set A, to do something in terms of some multilinear expression in terms of functions. So a stronger version of this theorem, which also appears in that paper, is the following. Okay, so any m+1 functions from this field to the unit disk. Look at the average. It should be, the main term should be the product of the averages of all these different functions. And then with an error term of size q to the minus n. So the important thing for now in interpreting this statement is this multilinear average here is essentially the product of the averages of the functions, and then some term that goes to 0 as the size of the field grows. And so again here, I should be assuming that the characteristic of this field is sufficiently large. So same C and gamma. Okay, so this now looks fairly reminiscent of an earlier result in ergodic theory that says something about what happens in totally ergodic systems. So I want to view this as some sort of finitary version of the following theorem due to Francis and Kra from 2005. We take a totally ergodic system, and I'll take polynomials as I did here, linearly independent. And for now, I'll stick with this assumption that they have 0 constant term. Then for any bounded functions, if I look at a multiple ergodic average corresponding to these polynomials, there will be some kind of asymptotic independence. So let's see, one. This expression converges to the product of the integrals of the functions fi. That converges now too. Okay, so if I took this whole expression and integrated against another function f0, this looks essentially like this result. That we have some average, some polynomial, in this case, a polynomial ergodic average converging to product of integrals. And
was there a weaker form of, or was there a version of Sarah's result with a worse error term known before? So it seems like the quantitative control on the error term is what's really cool about this.
So this result here, if you just want to say little o of q, that was previously known. Even this main term here was not at least previously written down, I don't think.
But should I think of this ergodic thing as just giving you like a 1 plus little o of 1 estimate? I mean, or
yeah, sure. Yeah. So yeah, so right, I should say this does not imply this, right? If it did, they wouldn't have taken 14 years to write it down. Then there's really new things happening in her proof here. But this, I think, is maybe useful heuristically for guessing why this result might be true and might be plausible.
Maybe wanting to remove p of 0, 0.
Yeah, so then I have to change slightly what I mean by linear independence. So that's this, I'm gonna keep it there for now, just to avoid having to define nastier things. Okay, so now I want to, right, so this looks like this, but there's an assumption here that the system's totally ergodic. So that's going to be, what I describe next is why are fields exhibiting this totally ergodic behavior, and then maybe we can use that for other combinatorial, interesting combinatorial things. So maybe just as a reminder, what does it mean for a transformation to be totally ergodic? Okay, let me write down a bunch of equivalent statements. So one statement is that every power of this transformation is ergodic. I'm going to rewrite that same condition in a slightly maybe strange way that will hopefully become more motivated later in the talk. If I look at the action along some ideal in the integers, I want this to be ergodic. This is ergodic for any finite index ideal in the integers. This is really just rewriting this statement in a less clear way, but maybe more generalizable way. Okay, and maybe the way to think about this statement is that T has no non-trivial periodic factors. So if there's any factor of this, so maybe I should say x mu t. Any factor of the system that's periodic, it has to just be the trivial system. And okay, there's some polynomials happening here. And so this last thing will explain maybe why total ergodicity relates to polynomiality. So equivalent to all these statements is that for any polynomial, I guess I should say that's non-constant, and any bounded function, the ergodic averages along this polynomial converge to integral of the function. So if we look at the action along this polynomial, it looks ergodic. Okay, so maybe this last statement is really the role that total ergodicity is playing here.
Is there a simple example showing that if it's not totally ergodic, you can find the polynomial? Is it just like a monomial then?
Yeah, so, right, I mean, I can just take my polynomial to be n times x, and then it's this statement.
Ah, got it. Okay. So the interesting direction is the other one, and you can just use van der Corput or something, or?
Exactly, yeah. So this direction is just take some maybe trivial polynomials, but going from ergodicity of this to ergodicity along polynomials is the way I would do that, at least, is using van der Corput. Okay, what things to say next, right? Okay, so total ergodicity is really important. So this statement here, so why is some aspect of total ergodicity appearing in finite fields there? So that's what I want to maybe see through something in here. define some notion of asymptotic total ergodicity that can help to explain that result. So let's say we have some finite commutative ring. Then I can consider the action on itself. So R is going to act on itself by translations. And if I take any ideal in this ring, that's going to give me a periodic factor of this system. So I can look, so let's say I is, okay, I should take a proper ideal. Then I have the natural projection map to this quotient ring. And let me call the action downstairs T tilde. If I take any element sitting in this ideal, then in this factor here, T tilde along multiples is going to act trivially. So maybe I want to write this instead. And so point down here is just some coset of the ideal, and my action is just shifting. This term here belongs to the ideal, and so this is the same as T tilde R. At this point. And so the action on this factor space is periodic, d-periodic for every d in the ideal. So if we have ideals of this ring, we can produce some periodic factors along elements of this ideal. Now, of course, the ring itself is finite. And so saying that we can't forbid finite factors entirely because our entire space is finite. But for some asymptotic notion, we just want finite factors to be getting larger and larger. So I'll say, I'm going to define some quantity here. So for now, you can think about LPF as standing for least periodic factor. So the size of the smallest periodic factor for this action, which is going to be the minimum index of a non-trivial ideal of R. Smallest index of a proper ideal. I guess I should say, if I had some periodicity, I could look at the principal ideal for my periodic thing, and that would get me a factor of this form. So these are really the factors to worry about. And I'll say that a sequence of rings is asymptotically totally ergodic. If this quantity is growing to infinity. Right, so over here I said that a system was totally ergodic if it had no non-trivial periodic factors. It's asymptotically totally ergodic if those periodic factors are growing to infinity. I think this is maybe a reasonable way to express asymptotic total ergodicity, and we'll see there's also actually a useful way of expressing it. So let's look at some examples, since this was maybe some abstract nonsense here. Okay, so one thing we could look at is say modular rings, integers mod n. In this case, the the size, this way. So the size of the smallest periodic factor is the least prime factor of n. So now I'm going to conveniently use this abbreviation for another thing also. So this is the smallest prime such that p divides n. Okay. And this is because the ideals are just going to correspond to divisors of n, and so this is the smallest divisor. Now another good example is if I take a field. Well, if I have a field, then the only ideals are the whole field or 0. And so the smallest index of a proper ideal is going to be just equal to q. And so at least from this definition, if I take finite fields that are getting larger and larger, this should be somehow approaching total ergodicity. And at least these results up here suggest that in some case, at least, that's meaningful to think of. Okay. So now the question is, can we drop some assumption in this result? So up here, we had to assume that the characteristic of the field was sufficiently large for something to kick in. So the thing that actually matters is for the size of the characteristic is these polynomials are having coefficients over the integers. So to make sure that they're actually non-constant and linearly independent, you need to be working in sufficiently large characteristic to see all of the coefficients. And the other place where characteristic is used is to make sure that the degrees of all these polynomials are smaller than the characteristic. So certainly the first one, you're not going to be able to get rid of if the coefficients are trivial and low characteristic. There's nothing you can do. But the real question is, can we do something where degrees of polynomials are higher than the characteristic? Let me write that down. So particular these polynomials have degrees bigger than the characteristic. So this I'm not going to directly address right away. The answer, if I don't make any changes, is no. The characteristic assumption is actually important if you just deal with linearly independent. I'll get there, but I want to start with just a single polynomial and looking at this characterization of total ergodicity. So can we understand some polynomial averages with asymptotic total ergodicity? And really, my interest is going to be finite fields, but now with low characteristic. And so our setting now is going to be larger and larger finite fields, but with the characteristic fixed. So I'm going to fix a prime key, and we'll consider these finite fields with k growing. And now ergodic theory of actions of the integers is not going to be very useful for describing the situation. So up here, I think this was actually a reasonable analog. If the characteristic is growing, it's sort of approaching a characteristic 0 objects, which maybe the integers are the right thing. Here, the characteristic is fixed at p, and so whatever this can be seen as approaching is not going to be the integers. So I'll just skip to the punchline. The infinitary object that we want to consider object to consider is going to be the polynomial ring over finite field with p elements. So why is this? Because all of these are quotients of this ring. So if I want to look at finite field and characteristic p, I can see this as a quotient where q is irreducible of degree k. Okay, so to get some heuristics to guess what the right result should be for finite fields of fixed characteristic, I'm going to move to ergodic theory of actions by this ring here. So let's move over here. Okay, so here's a theorem about polynomial ergodic averages for actions of that ring FPT. And I guess I should define, here. I should define what it means for an action of this ring to be totally ergodic. And depending on which version we use at some level here, we might get slightly different notions. But what I'm going to use is essentially this one here. So I'll say that a PT system is totally ergodic. This is ergodic. Every now and then. So I have an action of ft by measure preserving transformations on some probability space. And now when I look along here, I've been really looking at principal ideals, which all have finite index in this ring. When I look along these ideals, the action is ergodic. So I don't have any non-trivial invariant functions. Okay, so that's something, I mean, if you want, this is something about an ergodic theorem holding along linear polynomials. And so now we want to upgrade to some kind of ergodic theorem along higher degree polynomials. That's what I'm going to say now. Okay, yeah, so F here is just some finite field. They don't really care if it's a prime field or not. If we're ultimately interested in examples in these fields here, then take it to be F. But what I'm going to say doesn't matter. It doesn't matter so much. So let's say this is a totally ergodic action. Okay, and then for any polynomial, with coefficients in our ring, any bounded function, we want something off the ergodic average. Okay, so we're not going to get convergence to the integral of f. We're going to get convergence to a projection. So I should say what's going on with this average here. Also, Q here is the size of the field, and the sets I'm averaging over are monic polynomials of degree n. Okay. I can actually take any Fulmer sequence here, but just for concreteness, I'll take this one since it's understandable. So now my ergodic average converges to some projection of f, and it's an invariant space corresponding to these polynomials. Okay, so this is a little bit more complicated than what it looked like for z actions, where along polynomials, the convergence was just an integral of f. And the reason is that once the degree of this polynomial is bigger than the characteristic of the field, you can actually get non-trivial projections here. But it's still a projection. So that's really the core of total ergodicity, is that the limiting behavior is that of a projection. And this will fail. So again, you can characterize asymptotic, or you can characterize total ergodicity by saying that the limit of all of these operators along polynomials converges to projection for every polynomial.
If the system is not totally ergodic, then it may not converge to a projection.
Yeah. So that should be possible to see already from polynomials just being submultiples. I don't mean that's not quite true because you still have the ergodic theorem. Yeah, so yeah, you do need polynomials that are not linear in order to get failure of projections. The thing maybe to think about is that already for integer actions, if my system's not totally ergodic, not only is it not integral of f, it may not be a projection. So if you look along n squared for rotation on 3 points, you get things are unbalanced with it. It's not going to equidistribute. It's going to spend a third of its time at 0 and 2/3 of the time at 1.
Okay, but could you characterize still the limit somehow in theory?
Yeah.
So it would
In some way. I mean, so because this is a single operator here, you can use spectral theorem and say something about equidistribution of this polynomial. And what's important for it to be a projection is that the polynomial, even some polynomials are going to distribute in subgroups and not finitely many cosets of subgroups.
In principle, it can be done through some subtori or some properly defined tori, and then it will be familiar to Zedish.
Yes, I think if you just look for something like n squared, being a projection is going to tell you something about the spectrum of the system. Okay, so This result in this form was new from our paper this year, but the proof, we didn't prove much new to get this. So the proof, as I said, since we have a single operator here, you can use spectral theorem for unitary actions of this ring. And then it becomes a question about some equidistributional properties of this polynomial. And so this uses wild type equidistribution theorem due to Bergelsen and limN. Okay, and so because this goes through some spectral argument, we can also say when this projection does become the integral of f. For that, I'm going to need some definitions. I'm going to look at characters here. So just thinking of the group structure here, I don't care about this respecting multiplication or anything like that. So a homomorphism from this as a group to the unit circle. I'm going to say that this character is rational if there's some m such that this character is n periodic. And then irrational if not rational. And then we can say that a polynomial is good for irrational equidistribution. If something happens, so I'll do the same averaging again. Any fullness sequence will work. I want this to converge to 0 for every irrational character. Okay, so then what's going on here is that if P is good for irrational equidistribution, then this subspace is just constant functions. And so pi P, it's just integral of whatever function. And depending on how I do quantifiers, this characterizes being good for irrational distribution. So then I need to quantify over all systems and say that in every system this happens. Okay, so really the reason that this is more complicated is that there are polynomials here that are not good for irrational equidistribution. If you remember Wiles' equidistribution theorem, in the integers, if I take any polynomial, any non-constant polynomial, and multiply by something irrational, that is going to be uniformly distributed mod 1. And so the version of this for characteristic 0 is sort of uninteresting because being good for irrational equidistribution doesn't really, it's essentially a vacuous property of a polynomial. Okay, so right, so now I want to take this result here and put it in some finitary setting where asymptotic total ergodicity is coming into play. So some ergodic theorem that holds in totally ergodic systems naturally leads to at least the results to guess in a finitary situation. So let's see. Let me add to the examples over here. Notation. I want to look at quotients now of this polynomial ring. So I'll just do ft sub q to mean this quotient ring. And here, the size of the smallest periodic factor is going to be the least prime factor of q. So this is going to be the minimum of q to the d, where r divides q, r is irreducible, and r has degree. So the periodic factors of this ring here are going to correspond to factors of the polynomial q in the polynomial ring ft. And so the smallest one is going to come from irreducible factors, and the index corresponding to some irreducible factor of degree d is going to be the size of the field to the d. So that's where this is coming in. This is essentially the same as what was happening. Okay. So now let's state an asymptotic version of this result here. Let me take a polynomial with zero constant term. Any q. So I'll use the superscript plus for monic polynomials, which are maybe the right analog in the setting to natural numbers. And if I get rid of that, it's like the integers. It doesn't really matter. The point is just if I'm considering a quotient ring, multiplying the polynomial by some constant isn't going to change what that quotient ring is. So it's reasonable to identify them with monic polynomials. Okay, so for any monic polynomial and any function on this quotient ring, actually I go complex numbers. So I want to look at something like an ergodic average along the polynomial. And ideally, this should be converging to a projection of the function to some space of invariant functions. And so that's something right here. And this should be happening in the L2 norm. Okay, so what we get is that this is bounded by, let's see, I'll put the constant terms. Okay, so we have some polynomial average. This is the projection, and then we have something that if the least prime factor is going to infinity is going to go to 0. I haven't said what all of the constants here are, so let me do that now. So HQ is the subgroup of the additive subgroup of this ring generated by the values of the polynomial. And so this expression here is really the projection of the function f onto the corresponding space of invariant functions. And then these constants, so d is the degree of the polynomial, and this k that's appearing in the exponent and in the constant term is a related quantity. All the derivational degree of the polynomial, and I'll say what that is in a second. But it's always going to be bounded by the degree also. So if you want to just replace k's by d's, that's still a valid statement. Okay, so I think this gives some additional justification to defining asymptotic total ergodicity. So now we're thinking of the ergodic theory of FT actions, and the important quantity for the behavior of some polynomial averages in quotient rings is about this size of the least prime factor of Q, which was the quantity appearing in the definition of asymptotic total ergodicity. Okay, so right, let me say, so this derivational degree is, I'll say it's bounded by k if when I take enough differences here it tells it. Taking some differences, and if I have several parameters, this is just iterating this. Right, so you're thinking about this as, so it's called, this is the derivational degree because it's about how many derivatives of my function I have to take in order to reduce to 0. And I think I did things right, right? So a polynomial should be quadratic if its third derivative is 0. Okay, so that also maybe gives you a clue about how to prove such a thing. It's going to involve some van der Korpeting, and the number of times to van der Korpet is based on the number of derivatives we need to reduce this to maybe linear here. Okay, so yeah, so let me state some combinatorial applications of this, and then what happens with several polynomials, and I guess that'll be my time. Okay, so the first one, I'll call this Sárközy. So if I take a polynomial that is intersective, meaning it has a root mod q for every monic polynomial q. And then I take a subset of one of these quotient rings that does not contain 2 points whose difference is a value of this polynomial. Then the set can't be very big. So this has to be of size 2 times least prime factor 2 minus 1 over 2 to the k minus 1. And where intersective is used is, well, okay, so if I had 0 constant term, I get a projection here. Actually, for any intersective polynomial, I'll have a projection here because whatever constant term I have will necessarily belong to this set. Okay, but maybe a more interesting statement is the following. So now with some equidistribution assumption, then we can prove a result like this where A and B are coming from different sets. So I'll illustrate it this way. Any 2 sets A and B whose difference is a value of the polynomial. This is going to be what I should get size of A times size of B, and then some term here. That's a lower order. Okay, so you could get from this then a statement like this, but instead of A and B being in the same set, they're from different sets. And in fact, this result characterizes irrational equidistribution. So if you have some polynomial that's not good for irrational equidistribution, then at least for some conveniently chosen things to quotient by, this result will fail. Oh, sorry, this should not be Q. It should be, so it should be size of Q squared, and then least prime factor. Okay, so we can get some fairly strong combinatorial results from this viewpoint using asymptotical ergodicity and something coming from infinitary mathematics, which is equidistribution, or some results about ergodic theory. And so let me just state what the right version of Sarah's result is in low characteristic. I'm going to take several polynomials. Let me maybe just take them. P coefficients, you can do something a little more general, but since I'm stating it for fields, this is maybe the right thing to do. Suppose that for any characters, not all of which are rational, distributional behavior. So I'm just going to pose some equidistribution assumption on this family of polynomials, and then the conclusion is quite strong. So then for any f1 through fm, taking values in the disk and on some finite field of characteristic P. If I look at some multiple polynomial average, it's going to converge to the product of averages. Is bounded by the size of the field to the minus gamma. So really I should say here, there exists some positive gamma depending on these polynomials. And okay, so then you get the same sort of power saving bounds for similarity as a consequence of this result. And if you do not have this equidistribution assumption, the result is no longer true, which you can see just by taking these functions to be characters. So this is, again, sort of characterizing equidistribution in terms of some limiting behavior of polynomial averages. So this you should see as a low characteristic version of Sarah's result. Okay, so I think I'll end there.
Okay, are there any questions?
What's gamma?
Something potentially very small. So it's going to depend on how many times I have to do van der Korpening to reduce everything down. So
You can make it depend on degree when the
let me see, what's the dependence? So it will depend on, yeah, degrees, the number of polynomials. Yeah, I think I can get some explicit control on it that's maybe double exponential in some parameters. But I'd have to check. I don't remember exactly what we get. But its dependence on the polynomials and the degrees can be pretty bad. It's definitely not 1/2 of that.
It doesn't depend on K.
no, it does not depend.
Right. It does not depend on K. Otherwise, this would not be very.
You don't take a product there overall.
Oh, yes, I did. Yeah, so this is like some multiple polynomial average converging to product of integrals, and the error term is even a good error term, which is just sort of an automatic outcome of the method.
All these theorems, how much can you extend beyond x plus a polynomial, which vanishes?
You mean what besides?
No, what kind of other polynomials? I mean, it's a general philosophical question.
You mean, so they're putting some polynomial
Yeah,
variables here?
General there.
Yeah,
No, two variables, whatever we can, but maybe you want not polynomials, but other functions.
Now, the X. Eyesight is not very.
Like not translation and variable.
Yeah, not translation, but it's X and P of Y, right? Okay.
And instead you want some polynomial of x and y.
Yeah, so I mean, this is set up for Van der Kolk.
yeah, so I think, right, for me, because I'm thinking about this dynamically, X and Y are really totally different objects.
Yeah, right.
Right, X is coming from my probability space and Y is coming from my action.
Which, so, I mean, it's a Van der Kolk extension of all these Simoretti, but can we start to see something which is genuinely polynomials in several variables where X is playing the same role as Y? I mean,
Right, probably this dynamical
Yeah.
approach is not gonna be there.
If you have like a small enough number of functions relative to the number of variables, you can just Cauchy-Schwarz.
And assume independence.
Yeah, and they're sufficiently independent. But then if you have like 10 different polynomials and 2 variables, even if they're independent, like I don't know how to do it.
Maybe you have 4 polynomials into variables.
Um,
It's actually close to the.
yeah, that's like the threshold.
Yeah. 3 for sure.
Yeah.
So the proof of this theorem, am I right? It has little to do with the proof of these other theorems.
What do you mean by these other things?
This is single recurrence as
Yeah.
multiple recurrence.
Okay, so the proof of this theorem uses that theorem as a black box as the base case for some induction. So we use some version of this degree reduction technique. So we need some equidistribution as input, and we need that these kinds of averages are controlled by some Gowers norm. And then we basically just run it through a machine and get this as an output. So we have the equidistributions coming from that, and then Gowers norm controls coming from pet induction.
I mean, the reason I asked my question, if I may go back to philosophy, maybe Vitaly has a view here, is all this Cauchy-Schwarz and Gowers norm, Furstenberg, Simoretti, that it's all linear equations except for this Van der Kolk, which allows you this version of a nonlinear equation. If this was born from the circle method, which is 3-term progression, that does generalize to polynomial methods, to higher degree polynomials, if you have enough variables. It's robust in that sense. There's nothing linear about the circle method. But you can solve cubic equations in 10 variables and find solutions. So I'm trying to understand whether these methods are never going to go beyond linear other than this device.
But you see, it's multiple recurrence, so it's patterns made. You see, this one, the first.
Yeah, but you have to have the X variable. You have to have one variable, which is.
Yeah, but the point is, it's so to say single recurrence. So here there is a chance by different methods to get instead of X by some polynomial of 2.
Yeah, this is much closer to just
Right.
Fourier analysis.
But there it's patterns made of, in this case, what M items. So.
Yeah, well, if suppose you take a very strange view that I do of your subject, that is that let's say in a Grado for Davenport or somebody proved, I like to go to the prime application, let's say, that you can solve one linear equation with 3 prime unknown. Then if you try to do with the circle method more linear equations, you run into trouble. You need more variables, and this is where the ergodic methods of Furstenberg et al. Are so powerful. For linear patterns, then you don't have to suffer from the curse of the number of variables having to grow. But the circle method will always handle anything, even if the number, as long as you have enough variables, you can do non-linear equations. So then you and Liebman come and generalize Furstenberg and so on to these kind of situations. You might wonder that maybe one day somebody can combine and do something which is genuinely non-linear by these methods, or is linearity built into the Cauchy-Schwarz? So the circle method is more robust, right? You know, you can solve high degree. And somehow this method, which goes from a circle to a torus, of course, is within the circle method, but then to these characteristic factors and these multiple. Somehow, is it really merit? Is it ever going to break away from linear? And you'll tell me, and I would have said no, but then look, you've got something non-linear here. So I'm just trying to understand where this might. It's always good to also show the limits of what you do and not just say that, I don't know.
No,
You've got to stand up and say what we can't do.
Linearity stays. The moment you want everything non-linear, it will be close to Oppenheim's business of Margulis.
Yeah, but then it's a different game. Yeah, and then that's only quadratic that's successful there because there's an orthogonal group acting. So the non-linearity is handled still by linear groups.
Right. So if you want to stay dynamical but want quadratic, go to homogeneous dynamic.
Okay, but that's very limited to quadratic.
That
doesn't go to cubic.
No.
So I'm just trying to, yeah. I mean, sometimes it's very good to, especially if you like leading the field here, to explain what we can't do.
So that no one tries.
No, you shouldn't be dogmatic. You can't.
No,
but what, a test case of what. So remember when Langlands here stood up and explained that endoscopy can only do this, but nobody else wanted to say it. He had to say it, and then that kind of put a big damper because that's all right. We can't solve most of the problems that formulate. Then he put a very good reason, and then started to look at what is now known as beyond endoscopy. So maybe it's time to also understand the limits of this method, which you know, but maybe an outsider like me doesn't know.
No, I think you put your finger on the correct point. We are separating X and Y in their role.
Yeah, in that case, yeah.
And because it comes from an attempt to create Ramsey theoretical patterns by orbits. So X is the start of an orbit. If you are lucky to get polynomial orbit, you get it.
Yeah, I think right. The reason that we have some X and Y living in the same space is a coincidence of the setting we're in. That right, X is just some point. We aren't using any sort of algebraic structure of where X is living.
Yeah.
And then what is curious and what Ethan stressed here is that under assumptions of independence, you get really strong savings. But that's, of course, local to what we can achieve. Bigger thing about these polynomials of many variables replacing separation of X and Y, I think it's super chill. Super chill.
You don't have translation invariance and you can't do pet induction. You can't even really get started.
Yes.
But so if you want to stay at least morally ergodic, do from ergodic theory some combinatorial treatment and then apply it to those, right? So combinatorics may do it then, but this combinatoric itself, visually, could be a result of ergodic approach.
Are there other questions? Let's thank Ethan again.